Today we're doing 10.3 types of crystalline solids.
The first type of crystalline solid is molecular solids, which have only nonmetals.
The next type is ionic, which have metals and nonmetals.
The next type is metallic.
Yay!
I did it!
The last type we're going to learn about is network covalent solids or macromolecules. And we're going to have some pictures of these. We're going to have a table of data on these. Lots to learn. Okay, so here's a big summary of all the different types. Okay, so we have the 4 types we just mentioned. They're listed down the left, and I've given you some examples. The formatting here was a little funny. The 4 should be a subscript and the 3 should be a subscript, but I couldn't make that happen. And here we have SiO2, silicon dioxide, which is actually like glass. That's Erica coughing in the background. And these are ordered from lowest melting temperature to highest melting temperature. With these 2, the metals and the ionics, they're roughly in the same range, so I would never have you compare the melting points of those 2 with one another. But you could compare a molecular substance with a network covalent solid, and you should know that the molecular substance has a lower melting point. For the network covalent solids, you have to memorize that graphite or diamond, both carbon, pure carbon, and silicon dioxide are network covalent solids. And in the last column, we have the forces that you need to overcome in order to melt. So for molecules, you would check if you have dispersion, dipole-dipole, or hydrogen bonding. That was the lecture we did last time. Erica is cracking up in the background. For metal substances, you have to break metallic bonding. For ionic compounds, you are breaking ionic bonds. And we had an equation earlier that the lattice, well, we had energy is proportional to the charges of the positive and negative ions divided by ladies, divided by the radius. So let's erase all of this mess over here so you can actually see the equation. So when we're looking at ionic compounds and thinking about melting points, you want to look at the charge magnitude, the absolute value of the charge, and the radius of the ions. Okay, and the last thing for network covalent bonds, you have to actually break covalent bonds. So first we're going to look at some models of molecular crystals. And what you should notice here is this would be one molecule, this is another molecule, here's another molecule. In a molecular crystal, the force that's holding the different crystals together in this the different molecules together, in this big structure, would be intermolecular forces, the little green dots on here. So I've just circled those in blue. So these green dots would be your intermolecular forces holding 2 separate molecules together in the very large crystalline structure. So you'll see how all the molecules are organized around one another. So there's your big crystal. And the molecules are being held together by intermolecular forces. Here's another example. This would be iodine. So we have an iodine molecule, and then the molecules are held together by intermolecular forces. For iodine, iodine is nonpolar, so the only thing holding these molecules together in a crystal solid structure would be London dispersion forces. Hopefully you have that. The next thing we're going to look at will be metallic crystals. And in a metallic crystal, we talk about a sea of electrons surrounding positive ions. A sea of electrons surrounding positive ions. So on the left side here, these would be our positive ions. These would be the core electrons and the nuclei of each metal atom. And then the red dots that you see here, which I'm going to now surround in blue, the little red dots would be your valence electrons. And the valence electrons can move around. They are the sea of electrons. They're free electrons from the outer shells of the metal atoms. So the core of the metal atoms would end up with a positive charge because the valence electrons are floating around. Now the model on the right side is showing how those electrons can move. They don't move only in this little tiny space. They're actually moving all around, all over the place. But again, we have our positive metal ion cores, and then the valence electrons are floating around in this sea of electrons. Okay. Now we have models of ionic crystals. Ionic compounds, when they're in a solid crystalline form, are very, very ordered. All crystals are very ordered, but you'll see this is a model of sodium chloride. Both of these are actually models of sodium chloride. And we'll have chlorine, sodium, chlorine, sodium, chlorine, sodium, chlorine, sodium, chlorine, sodium, chlorine, sodium, chlorine, et cetera, et cetera. It's called a crystal lattice structure. And again, in this one, we're just separating out the ions, a little bit. The greens are your chlorides, the blues are your sodiums in this model over here. So your ionic crystals form an ion right next to another ion. It goes ion, ion, positive, negative, positive, negative, positive, negative. The last set we will look at is network covalent solids. And in these, you'll notice we don't have single molecules that are just held together by intermolecular forces. You have single atoms that are all connected to some other atom in the structure. And all the atoms are somehow interconnected. So this atom and this atom way up here, there's no intermolecular force. There's covalent bonds. There's a bond here, a covalent 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 bond here. So ultimately, the atom at the bottom and this atom up at the top, in order to get those atoms broken apart from one another, we literally have to break covalent bonds. We've got to break all these bonds. Well, there's a lot of energy needed to break a covalent bond. See, all these bonds have to get broken in order to melt this substance. And because all those covalent bonds have to get broken in order for the substance to melt, this substance has a very, very large melting point. Okay. Oh, and just so you know, this is actually diamond. This is a model of diamond. On the right side, we have a model of silicon dioxide. And again, you'll see we have these covalent bonds, and we have to break all these covalent bonds in here in order to melt this silicon dioxide macromolecule. And silicon dioxide is just glass, SiO2. It has a macromolecular structure where every atom is somehow bonded to some other atom in the structure. And again, in order to melt, we have to break every single covalent bond, and there's a whole lot of covalent bonds that we have to melt in here. Oh my gosh, it's going to take me way too long to break them all. Lots and lots of energy. Whereas if we're talking about melting a molecular crystal, I don't have to break any covalent bonds. When you melt a molecular substance or boil a molecular substance, you are not breaking any covalent bonds. You are overcoming intermolecular forces. Okay, so in order to melt, you must overcome intermolecular forces. That means these green dots, we're overcoming the forces. We're not breaking the forces, we're not breaking any energy, we are overcoming these intermolecular forces that we're holding the molecules together. This doesn't take that much energy. Notice I'm slowing down and talking really slowly because we don't need a lot of energy. We can be lazy and melt our molecular crystals. And for our ionic crystals, we have to break ionic bonds to melt ionic compounds. And for metals, you have to break metal bonds. Okay, so we're going to do some problems now. Which substance would have a higher melting point? Why? First thing you want to do in all of these problems is identify what kind of a compound you are dealing with. You might want to write that down. You don't have to, but you must identify what you're dealing with here. So H2O, you look at it and you say nonmetal, nonmetal. This is a molecule. It's not one of our network covalent solids. So this is a molecule. This is an ionic compound. Therefore, LiF has a higher Tm because it is ionic, and ionic bonds have to be broken in order to melt this. And you should identify that water is molecular. End of story. Okay. H2O versus Cl2. These are both molecules. You should recognize this has hydrogen bonding because it's got H connected to O. Cl2, you should recognize that's a molecule. So we're dealing with molecular, intermolecular forces. This would be a nonpolar molecule. So you would write, water has a higher melting point because hydrogen bonding is a stronger force than London dispersion forces. You could add, since Cl2 is nonpolar, it only has London dispersion forces. Okay, number 3, neon versus chlorine. This is a nonmetal. So the only forces that this would have would be dispersion forces. Chlorine, it's a nonmetals only, it's nonpolar. It has only dispersion forces. So now we're dealing with two things that have only dispersion forces, and you have to say, well, which would have the higher strength of dispersion forces? It would be the one with the most electrons. So neon has 8 electrons. Hang on one second. They're not done. AP Chem is done. Chlorine has 34 total electrons. Hang on one second. And so, since both have only dispersion forces, chlorine has a higher Tm, higher melting point, because it has more total electrons. So now, rubidium iodide versus potassium iodide. You should recognize these are both ionic. So we have to identify what kind of a substance are we dealing with. Oh my gosh, ionic. So we want to think about the lattice energy is proportional to Q1, Q2 over R. So we'll look at our charges, +1, -1, +1, -1. That's not helping us at all. They have the same charge. So now we have to look at the radius. And we see, for the negative ions, they're both iodine, so that would have the same ionic radius. But rubidium 1+ versus potassium 1+, we would say, hopefully you'd recognize, rubidium 1+ has, let's see, it lost its outer shell. So it has 4 shells of electrons. Potassium 1+ has only 3 shells of electrons because potassium lost its outer shell. Therefore, Rb1+ is larger. Therefore, let's see, a bigger R means a smaller lattice energy, because if this denominator is large, then the lattice energy is small, which means you need less energy to melt, so that would be a lower melting point. So, therefore, Ki has a higher Tm because it has a smaller radius, because K+ has a smaller radius. And that would be enough to write. If you were asked, which has a higher melting point, why, you could just show this information right here. Show the charges, talk about the shells. Therefore, simple, easy. Okay, Rb2O versus Rbf. You have to recognize this is ionic, this is ionic. It's good to write these things down. So we're going to look at the lattice energy, which is proportional to Q1, Q2 over R. So we need to check our radii and our charges. So Rb plus 1, O negative 2, plus 1, negative 1. Oh, look at that. Now, we could look at our radii also, but if you look at O versus F, F is slightly smaller than oxygen, but it's not going to make a big difference. The big difference here is this plus 2 magnitude versus the plus 1. The charge on the O is double the charge on the F, even though F has a slightly, F1 minus has a slightly smaller radius than O2 minus. That is true, but the radius is just a small part compared to if we double the charge. We make this twice as big. Hopefully you see the tiny difference in radius definitely has a much smaller effect than doubling the charge. So we would say O2 minus has a larger charge than F1 minus. Therefore, the lattice energy for Rb2O is larger than for Rbf. Therefore, Rb2O has a higher T sub m, a higher melting point. Okay, oh, 2 more. Really? This just keeps going and going and going. Copper versus argon. You should look at this and say, okay, we've got a metal, we've got a non-metal, and that is not a network covalent solid. We don't even have to look at our intermolecular forces or anything like that. We just say copper has a higher Tm, higher melting point, because it is a metal. You want to mention argon has only weak London dispersion forces. You do want to identify the type of forces that each substance has. Okay, I'm going to change number 7. Carbon versus hydrogen. And what you have to recognize, this is one of our network covalent solids. This is a nonpolar molecule. Boy, is my voice sounding scratchy. Okay, let's get some energy back in here. So, network covalent solids. Carbon. Covalent bonds have to be broken. Covalent bonds have to be broken. Okay. So hydrogen only has London dispersion forces. Therefore, carbon has a higher melting point. Now, dissolving. One of the homework questions that's on the sheet I gave in 2012 anyway. Involved things, can they dissolve in one another? So the rule is like dissolves like. So polar molecules dissolve in polar molecules, nonpolar molecules dissolve in nonpolar molecules. Nonpolar molecules and polar molecules are immiscible in one another. Immiscible means will not dissolve. By the way, when we talk about this polar molecules dissolving in nonpolar molecules, if you have 2 molecules that have hydrogen bonding, they will dissolve in each other even better than just 2 polar molecules. Because hydrogen bonding is an even stronger intermolecular force, so the 2 things like each other even more. They're more liking of each other. There's a stronger force holding the 2 molecules together, so they're more likely to be dissolved in one another. Okay, so we're going to look at some problems. We're going to find out, are these things miscible in one another? Okay, so water and iodine. Miscible, by the way, means will it dissolve? Will the one thing dissolve in the other? So we want to know, will water and iodine dissolve in one another? So we look at the forces. We know that water has hydrogen bonding. We always look at the intermolecular forces. Iodine is nonpolar, so it only has London dispersion forces. It's nonpolar. Now, hydrogen bonding means extremely polar. That's like the most polar you can get. So this is very polar. So, will these be miscible? No. And your explanation would just be iodine is nonpolar, water is very polar, therefore these are immiscible. Okay, another one, water and butane. C4H10 is butane. Now water, it's very polar. We just found that out. We did that in the last problem. There's hydrogen bonding, it's very polar. C4H10, you do not need to draw this out. You need to memorize. Carbons and hydrogens. A CH bond is a nonpolar bond. So if all I have is carbon and hydrogen, I know that this thing is nonpolar. So, will this stuff dissolve in one another? No, it is not miscible. We have polar and nonpolar substances. So now we're going to look at an old AP question. If you want to try this on your own, just pause this and answer these on your own, but I'm going to do it right now. So first we're going to find the types of intermolecular attractive forces in pure glucose. Notice we have the OH here. Let me get to we have this OH. We've got a bunch of OHs in here. So this definitely has hydrogen bonding. Cyclohexane has only CH bonds. It's only got dispersion forces. Dispersion forces. Those are the only forces. Now let's go back up to glucose for a minute. If you're asked for all of the intermolecular attractive forces, when you have hydrogen bonding, you cannot mention only hydrogen bonding. Anything that has hydrogen bonding is also polar, and so the actual forces are dipole-dipole forces. So the molecule is polar, we have dipole-dipole forces. And all molecules have dispersion forces. Dispersion. Van der Waals, we can call it, or London dispersion forces. Now we know what the forces are in each of these two different molecules. All right, B. Glucose is soluble in water, but cyclohexane is not soluble in water. Explain. Okay, so we already found out water is polar and has hydrogen bonding. And then we want to say, like dissolves like. So water and glucose are miscible. Or you could just say, can dissolve in one another. Now, we said water is polar and has hydrogen bonding, and we just learned that cyclohexane is nonpolar. Water is polar. Therefore, these are immiscible. End of story. Okay, so here is a visual of how vapor pressure is actually measured. So if we have pure mercury, this is mercury. Whoa, sorry about that. There we go. All of this is our mercury. And we have a vacuum up here. Now, in the vacuum, we put a little bit of liquid water, and then we allow that water to come into equilibrium with its vapor. So water molecules will evaporate and go into this space up here, and it'll create some water vapor pressure. And notice the height of the mercury decreases. It went from 760 down to 736. So the vapor pressure of the water molecules is 24 torr. I'm not sure what temperature this particular experiment was done at, but you do this at different temperatures and the vapor pressure will change. It's very dependent on temperature. As temperature goes up, vapor pressure goes up. So we do the same thing with this ethanol vapor. We put ethanol liquid right in here. It was the green that was there a minute ago. Let's erase that so you can see it. And then some gas from the ethanol goes into the gas phase, and it creates a vapor pressure, a gaseous pressure, which is 65 torr at the same temperature where water would create a vapor pressure of 24 torr. And I'm not sure what this last chemical is, but it's something that is very, very volatile. Volatile means it's likely to go into the gas phase. So we put our liquid, the red liquid down, sitting down right there, and the gas molecules evaporate, come into equilibrium with the liquid phase. And here we have a very large vapor pressure at the same temperature as the water molecules and the ethanol molecules. So that is how vapor pressure is actually measured experimentally. And again, you can change the temperature and get the vapor pressure for different substances at different temperatures. So now we're going to look at changes of state, a heating curve, a solid going to a liquid going to a gas. Okay, I realized I could just use the book picture instead of my own. Now, we always start with the solid phase if we're doing a heating curve. Well, that's not true. We don't always start with a solid. But if there are two flat lines, then the first area is solid. This first flat line would be your T melting, because you're going from solid to liquid. And up here you have only a liquid present. Notice in this space where you have the flat line, you have a solid and a liquid in equilibrium with one another. A solid and a liquid in equilibrium. Hopefully you remember from last year or 2 years ago, equilibrium means that you have a reaction going backward and forward at the same rate, dynamic equilibrium. So the reaction here would be a phase change reaction, just a solid going to liquid, liquid going to solid. All right, so we are going up through the liquid phase, and then we flatline. A little bit too high there. There we go. We flatline. And that right there would be our T boiling, TB. So you can always use one of these curves to identify a boiling or a melting point. When you're boiling, you have the liquid and the gas in equilibrium with one another. And then when the temperature starts to rise again, you have only a gas. And this curve could be done as a cooling curve, where you start with the gas, and then you have the gas and the liquid in equilibrium. Only liquid, liquid and solid in equilibrium, and then solid. So this would be time, this would be degrees Celsius, that would be our T boiling, this would be our T melting. Gas, gas liquid, liquid, liquid solid, only solid. All right, last but not least at all, phase diagrams. On the left side, we have the phase diagram for water. On the right side, we have the phase diagram for carbon dioxide. In all phase diagrams, let's put this water here, CO2 here. In all phase diagrams, you'll be shown where there's a triple point. So on the right side, they're noting it over here. On the left side, if you want to identify it for yourself, you can point it in there. It's where the solid, the liquid, and the gas lines all meet. And you need to know the gas comes at the bottom right, over here. The solid is always on the left, and the liquid is in the middle. So we go solid, liquid, gas. Solid, liquid, gas. I'm going to say something that you might laugh at. I'm Okay, I heard this at an AP workshop. If you ever forget, you can remember the gas comes out of the butt. So if you think of this as a little butt and the fart is coming out of there. I can't believe I just said that on a YouTube video. But you know what? If it's going to help you learn it, that's a good thing. And it came out of an AP conference. And so, okay. One thing to note about these phase diagrams with water, whoa, sorry about that. The solid liquid line has a negative slope, and with CO2, the solid liquid line has a positive slope. Sometimes you're asked when you have a phase diagram, which is more dense, the solid or the liquid? So you just think at a certain pressure, pick any pressure. Pick a pressure. As pressure goes up, we are going to the liquid phase. Hopefully you know that as pressure goes up, that means density will increase or decrease? Increase. As pressure goes up, density should increase because the molecules should be getting closer and closer together. So liquid water is more dense than solid water. That's why ice floats on top of water, and it's a good thing because if that didn't happen, the Earth would not have evolved the way it did because ice caps would sink to the bottom of the ocean. And the ocean up in the North and the South Poles would freeze completely. And lakes that freeze in the winter would freeze completely and all the fish would be dead. So we're very glad that ice floats on water. Carbon dioxide, on the other hand, you go to your solid liquid line and you just make pressure increase, and notice we're going into the solid phase. So as pressure goes up, density will be going up, and we're in the solid, so the solid is more dense than the liquid. You should probably write down those words that I just said. And you can pause the video, play it back and forth a couple times if you need to, just to make sure you have that information. Okay, I've got one more phase diagram here. It's a made-up phase diagram. A whole bunch of definitions. I'm not going to go over all these definitions. They're just things you need to know. One of the keys is the line, this whole line, F, the liquid gas equilibrium line. That means solid, liquid, gas. The liquid and the gas are in equilibrium with each other everywhere along this line. The line for C, the solid and liquid are in equilibrium everywhere along that line. And along line G, the solid and the gas are in equilibrium with each other across that line. Okay, you also need to know the words sublimation, deposition, boiling, condensation, freezing, melting occurs along these lines. So, solid gas, sublimation, deposition. Going from solid to a gas would be subliming. This is solid to gas. Deposition, on the other hand, the computer is, there we go. Have to switch that again. Going from a gas to a solid is deposition. Hopefully you know that evaporation is going from what? Liquid to solid. So condensation would be going from solid to liquid. Freezing is usually called fusion in chemistry. So when you hear the word fusion, we're talking about freezing, which would be liquid to solid. Melting would be solid to liquid. Okay, a couple more terms. There's something called a critical pressure and a critical temperature. That's this point right here is called our critical point, H. That was given to you right there. Your critical temperature would be the temperature at the critical point. Your critical pressure would be the pressure at the critical point. So for this would be 4 atmospheres, and the critical temperature for this particular diagram would be 100. Do I not have units? That should be degrees Celsius. The normal boiling point is the boiling point when the pressure is 1 atmosphere. This particular diagram doesn't have a normal boiling point because at 1 atmosphere, we have sublimation and deposition going on. Let's look These two did not give you an actual scale, so we can't use those. But you would go to 1 atmosphere and then find the temperature at 1 atmosphere. So as an example, you go to 1 atmosphere and then you go down to the temperature. But let's just pretend, because we couldn't do it on this graph, pretend that 1 atmosphere was right here. Okay? So the normal boiling point. You go to 1 atmosphere, you go to the boiling line, which would be this line over here. You draw a straight line, and then you go down, and our T and B normal boiling point would be approximately 98 degrees Celsius. Again, that's if 1 atmosphere was right here. And then our normal melting point, T normal melting, you go to 1 atmosphere, and you go to the solid liquid line, which is where melting would occur, and you drop down, and we would be at approximately 19 degrees Celsius. Again, our scale didn't work to find the normal melting and normal boiling point for this particular phase diagram because 1 atmosphere did not have boiling or melting able to happen at that pressure. Okay, that's it.